e to the 2x over x, finding the derivative. Another quotient rule situation, so x squared on the bottom, low d high. Oh boy. Well, the surprise reveal hopefully will happen in a second. Either that or the whole thing's going to cut out again like it did yesterday, the day before, and the day before that. So 2e to the 2x is the derivative of the top minus high d low, which should just be the e to the 2x. All right, we have a common e to the 2x we could pull out. Now it's lagging on even on my screen. Like, try it again. There it is. E to the 2x. Pull out an e to the 2x from each term. I have a 2x minus 1 over x squared. It didn't ask us for anything beyond the derivative, but this is nice because if I needed to know the horizontal tangent, set my derivative equal to 0. If I needed to know a vertical tangent, I can start looking at the denominator and see what the limit of the derivative would be as I approach 0. You know, if it's going to the same kind of infinity or different kinds of infinities, it might indicate a cusp versus a vertical tangent. Right? So those concepts still are a thing, so we got to be careful about that. Number 8 doesn't have a base e, so that's a little bit of an issue because we don't have a rule for that as of yet, but there is a hint. It's the definition of a hint. The hint is supposed to kind of get you thinking in the right direction, it's not a process. A process will tell you what to do. A hint is to say, all right, so we want to try to make it somehow into a base e. Can we make the number 4 into a base e? Well, yeah. So e to some power, I'll call it a, would be equal to 4. I just got to figure out what that a is going to be. Once I figure that out, then I'll have some equivalent relation with a base e equivalent to 4. All right? That's one of those obscure topics in pre-calc that served or seemed to serve absolutely no purpose whatsoever except to get a question right, if it actually came up in pre-calc. So anyway, algebra 2. All right, so little Lagrangian action perhaps. So a equals ln of 4. Yeah, so in terms of conversions, I can never state this enough because it doesn't matter what class you're in. People historically just struggle with logs for some reason. Even the converting back and forth from one to the other. But generally, the biggest struggles come from knowing when a log is supposed to be involved in a situation. Right? It's like, oh, I didn't even know I was supposed to use a log there. Well, that's an issue. That comes with experience. But just converting from exponential to log form. The idea behind it is if I have an unknown exponent, a log is a technique that I could use. All right, so how do I convert to a log? Well, the base of the exponential function is the same as the base of the corresponding logarithm. So I know it's log base e. And there's all sorts of mnemonic devices, but the one I like the most is first establishing your base and then doing a quick switcherooski on these two bad boys. All right. The log base e is the same as the natural log, and so you can go right to it from there. You learn about things like Lagrangian DNA. You got the Ben relationship. Maybe you learned about that one. There's like a circular movement that you can get from one to the other. This is the one I settled in on as the best one. All right. But what that's telling me is that 4 is the same as e to the ln of 4. All right? So that's really the justification behind a property in pre-calc. I mean, algebra 2, yes, but pre-calc definitely, where it was like, here's another log rule. E to the ln of x equals x. Ln of e to the x is equal to x. You're like, okay, cool, that's great, and then you hardly ever used it. Okay, so here we're using it. And the reason why we're using it is because we know an awful lot about how to find the derivative when the base is e. We know nothing about how to find the derivative when the base is something other than e. All right, so I'm going to rewrite this as y equals e to the ln of 4 times x. When you have a power to a power, you just multiply the powers. So I'm going to write it as e to the ln of 4 times x. Under normal circumstances, I would write it as x ln 4, just for convenience sake. But in this case, I want to make it actually very clear that ln of 4 is a constant multiplier of x. And regardless of the fact that it's not the nicest looking one, it still would have the same role in a derivative that the number 2 would have, or a 1/2 or a pi. All right, ln of 4 is just a number. So when I take the derivative of this, dy dx would be e to the ln of 4 times x times the derivative of the exponent, ln of 4. Now we do know, because we came up with this, that e to the ln of 4 times x is the same as 4 to the x. We have a simpler form of the derivative. And also the basis of a rule. Because if you compare our derivative to what we started with, actually not too different except for the ln of 4. Right? And in fact, we had been following this rule the whole time, because what we were dealing with when we were taking the derivative, I missed. Let me just zoom back in a little bit. The derivative with respect to x of e to the u was e to the u times the derivative of my exponent. But without even realizing it, we were also multiplying by the natural log of e. But the natural log of e is what? 1. So it never worked its way into the solution. So d dx of some base other than e would have the same structure, but this time that ln of a, whatever the base is, would not just cancel away, because that a value is going to be something other than e. All right, so I mean, basically it's got to be something other than e or 1. Like your base of the exponential can't be equal to 1, because 1 to any power is 1, and it's not an exponential function. All right, but those are the only conditions that would require you to have something other than what we have here in purple. Now, these problems, numbers 9 and 10, they're kind of rehashing all the other stuff. You know, taking the derivative is not overly challenging. What I wanted to do is review how you would go about doing it on the calculator, just because people often forget that they have calculators, even on the calculator part of a test, exam, etc. They still default to a by hand approach, which is sad for me. Not sad for the student, because you're taking the test. You know, you're nervous. It's a test. That's what happens, right? But for me, it's like, it's supposed to be a gimme, and I was supposed to just put a check mark next to your question, indicating that you got full credit. But now I can't do that. I have to take off points, and I didn't want to take off points for anyone on this question. It was supposed to be a freebie. So how do we get our freebies? If you have your y4 in there, you really don't need to do much work. So y1 is your function. You don't even need to look at the picture. 2x plus 3. I mean, unless you suspect that there's some sort of discontinuity going on, or the point that you're given is outside of the domain, but exponential base e is everywhere continuous, and it's also, it has an infinite domain. It doesn't have an infinite range, but it has an infinite domain. So y1 is my set of coordinates related to the function. y4 would be the slope at any point along that function. So I go to my table. If you have to mess around with the settings, you mess around with the settings. But I'm looking at the x value of -1. All right, all I need in this one, because they're asking for the slope of the tangent line, is that number. All right. The only concern would be if a question calls for an answer in a particular form. So the slope dy dx when x is equal to such that x is equal to -1 would be, I'll put the approximate symbol here. All right, new prescription time. I got the 5.4. What are the two numbers after that? 366. That's so crazy. This is where I lose it. All right, that blows. So, anyway, you look at this and you say, well, that's wonderful. How can I get from that to an exponential e? Well, one way to do it would be to actually just do out the calculation, because it's not too bad. This is just 2e to 2x plus 3, plug in the -1. All right. Another way to do it would actually be to kind of play around with powers of e, but if the power is something crazy like a fractional value, then that's a different story. If it's a multiple choice question, then you're fine, because you just find the choice that matches 5.4366. Right? And so you'd be all right. But it's a simple enough derivative that we don't actually have to do it. 2x minus 4 is the exponent for the next one, and we want the equation of the tangent line. So same process, this time at the x value of 2, clean numbers, nice. So I know my slope is 2. So that's f prime of 2 is equal to 2. The coordinate 2, 1. Pull out that shape though. Oh, that's weird. Something about the 3 was pointing. All right, so 2 times x minus 2 plus 1. Yeah, there's nothing without them, that's obvious. Barely see it. All right, so yeah, it's just point slope form of a linear function. Pop it in, call it a thing. And point slope form is the way to go. No work required. Otherwise, you get to a point where you have to solve for a y-intercept, things like that. I mean, unless you want to put that y-intercept down. 0.01832. So you could conceivably do it that way. It's not as nice, but you could say y equals 2x plus, so that is the y-intercept, right? Yeah, suppose. Let's see how that's going to be equivalent, but it must be a rounding issue there. Anyway, the next one. That one looks like, oh, wow, crazy. Product rule, chain rule. Or possibly simple multiplication. Let's try simple multiplication first. So power to a power, multiply your exponents. E to the 4x minus 2 times e to the x squared minus x. Keep the base, add your exponents. All right, so e to the x squared plus 3x minus 2. Then we could take our derivative, which would be e to all that stuff multiplied by the derivative of the exponent, which would be 2x plus 3. I mean, product, chain rule, all that stuff, it'll work. It'll get you an answer. Yeah. Most people like my answer a little bit better. For this one anyway. A natural log. All right, so exciting times. Well, we could do the limit definition. We'd hit a roadblock almost immediately. Okay, so definitely not the way to go. You'll take my word for that, because all I would end up doing is showing you me plugging in x plus h for this, writing it in the difference quotient, and then saying, okay, now we're stuck. We can't do anything with that, so let's try something else. All right, so I kind of just bypass all that. Let me write this as y equals ln of x for simplicity's sake. All right, I don't know anything about the derivative of a natural log, but I do know how to find the derivative of an exponential function. And we can convert from log to exponential form, yeah? So x would be equal to e to the y. All right. So normally I'd be taking the derivative of a function of y in terms of x. That derivative would be noted as dy dx. Well, now it's a function of x in terms of y. So my notation should change accordingly. So dx dy. Independent variable is now y, with the dependent variable being x. What is the derivative of e to the y? E to the y. All right. Okay. Well, I don't want dx dy. Let me put that over a 1. Because, yeah, I don't want a dx dy, so let's make it a dy dx. I can't just flip one side, so let's flip the other side. Also, legal maneuver is basically a shortcut to cross multiplication. You can flip one side of a proportion as long as you flip the other side. You can swap diagonals any way you want. All right, that's all a result of the idea that you can cross multiply. By being able to cross multiply, it allows you to do all that stuff too. All right, so I need a derivative in terms of x, and that clearly has a y in it, so that's a problem, but an easy fix. Because e to the y is the same as what? X. Because it says that right here. E to the y is x. All right, so anywhere I have an e to the y, I can replace it with an x. So what we just got from this is, and actually much easier, I think, than using a limit definition, is that the derivative of the natural log of x is just a 1 over x. But the chain rule component of that has to allow for the fact that maybe it's not just an x that we have the log of. We have a log of a sine of x, log of anything of x, all right? But don't get confused by the fact that maybe sometimes it's just the log of 4, like on the previous page. If it's log of 4, it's not a function of x. So when we take the derivative, we're taking the derivative of a constant, it goes to 0. No rules need to apply other than the derivative of a constant, right? So we get our chain rule variation on this, which tells us that if we have the natural log of a function, that we would do 1 over the function just like we would do 1 over x, but then we also have to multiply it by the derivative of the inner function itself. All right. So natural logs, not too bad when you look at it from that perspective. Number 1 as a constant multiple. So 4 times 1 over x. Number 2, power rule, 2x, plus, well, natural log is just 1 over x. Number 3 gets a little juicier because we got a little bit of chain rule going on here, but nothing too crazy. So it's power rule followed by the derivative of the inner function. So f prime of x would be equal to, so something to the third becomes 3 times the something to the second power. And then we multiply by the derivative of the something. So 8x becomes 8. 3 ln of x becomes what? 3 over x. All right. So I mentioned before, don't forget that pre-calc is a thing. That's going to come up in number 4. It might have come up in number 3. I mean, I gave it some consideration, at least in my mind. It's like, sometimes I will look at it and say, is there any value to actually multiplying this out before I get started? Will it make my life easier? No? Okay, chain rule it is. Okay. If it is, I mean, if something will cancel away nicely, then yeah, go for it. But sometimes it doesn't. Sometimes you just gotta, crack the old knuckles and get into it, And then while you're at, elbows, knees, and neck, and toes, and when you're 40, you'll have arthritis. But you know what? You'll be good at math. So in the end, yeah, it's a good trade-off. Agonizing pain, but really solid understanding of math. So the pre-calc part of this, I could use some chain rule. I could do the 1 over u times u dx. But the natural log of a product, because we have product rule for derivatives, but we also have a product rule for logs. ln of 5 plus ln of x. The derivative of which would be just, well, ln of 5 is constant, right? So that goes away. ln of x is the only thing that's relevant, so 1 over x. Honestly, I only needed to do that once before. I was like, okay, so what you're telling me here is it doesn't matter if there's a coefficient of x. A numerical coefficient, it's still going to be 1 over x? Cool, got it. All right. And even if you use the u rule, it would be 1 over 5x times 5. The 5s are going to cancel anyway. All right. So when you get to something like this, it just became a whole lot easier. Because now we're looking at product rule, sure, but product rule where I already know what the derivative of the natural log component would be. So my first function, 3x squared, times the derivative of the second, 1 over x, plus the second function, ln of 4x, times the derivative of the first, which would be 6x. Which rule?
How do you know to add this?
Product rule. First times the derivative. Yeah. All right. Number 6 is kind of a trick question. Because a log exponent rule makes you think you could just hop it over. Because if it was just the x being raised to the power, then that'd be exactly what you do. But here it's chain rule. So 4 ln of x to the third times 1 over x.